Chemical Equilibrium Part 6, Heterogeneous Equilibria. So what is a heterogeneous equilibrium? And basically, it is a system or a chemical reaction that is at equilibrium that has more than one phase present. So for instance, if we had a chemical reaction where we had both solid present and gas, that would be a heterogeneous system. Now, we can calculate equilibrium concentrations or partial pressures for heterogeneous equilibria just like we do for homogeneous equilibria. However, there's one big essential difference in these calculations, and that is when we write the equilibrium constant expression for a heterogeneous system, the activity for all solids and pure liquids present is going to be equal to 1. So the activity for any solid or pure liquid is 1 in the equilibrium constant expression. So how does this work? Let's look at our generalized reaction that we've looked at before. And both reactants are aqueous and one of our products. Our other product is a solid. So how would we write the equilibrium constant expression? So it would look very similar. Products over reactants, with each individual reactant or product raised to the power of its coefficient, and then we would put 1 in for this pure solid. And of course, doesn't matter what the coefficient is because 1 to any power is still just 1. So that's the equilibrium constant expression for a heterogeneous system. So let's look at a real heterogeneous system. And we're looking at the decomposition of calcium carbonate solid. And it decomposes into carbon dioxide and calcium oxide solid. Let's say that we put some calcium carbonate in a sealed container, right here at 25 degrees C, so we just have a pile of it at the bottom of the container, and we're going to let time pass. And after a certain amount of time, we're going to have an equilibrium set up. And in this case, we are going to have calcium carbonate and calcium oxide mixed together, both solids at the bottom of the container, and we're going to have carbon dioxide gas at some partial pressure inside this container. Now, how would we write the equilibrium constant expression for this system? We would do it the same way that we've been doing it, so products over reactants, partial pressure of carbon dioxide, calcium oxide, which of course is a solid, so we're going to put in 1, and calcium carbonate, which is also a solid, so we're just going to put in 1. It actually greatly simplified our expression. Now, the interesting thing about this is that it doesn't matter how much calcium carbonate we start with. The partial pressure in our closed container at some given temperature is always going to end up to be the same. So we can have a little bit of calcium carbonate, or we can have a lot of calcium carbonate, and it doesn't matter. All that matters is that in this container, at some given temperature, when it's closed, it's going to set up the same partial pressure, whether there's a lot of it or a little of it. We can use ice tables to organize our information for heterogeneous systems in a very similar way to our homogeneous systems. And so let's go ahead and look at an example using an ice table to solve an equilibrium problem for a heterogeneous equilibrium. So what we're going to do is put calcium carbonate in a closed container. And at some temperature, the equilibrium constant for this reaction is 1.04. Now, we want to determine the partial pressure of carbon dioxide once the system reaches equilibrium. So how do we start? Basically, again, it doesn't really matter how much we started with. So I'm just going to leave that blank. You could write some in there if you wanted to, but basically it doesn't matter how much we start with, so we can leave it blank. What we do know is that we start off with no carbon dioxide gas. And it's important to write that in there because we're going to use it to figure out our change line. For the change line, we know that the system has to go toward the side where there is none. So we have no carbon dioxide. Initially, the system is going to shift in the direction of products to make carbon dioxide and calcium oxide. And so, again, on the change line, we can either write nothing because we already know that this activity is just going to be 1 in the equilibrium constant expression, or we can just write down, just to keep track, that we used some, and we used it to make carbon dioxide and calcium oxide. We made plus X of carbon dioxide, and this is exactly what we did before. So the coefficient for carbon dioxide is 1, and the equilibrium is shifting in this direction. And then we also made some calcium oxide, but again, it doesn't matter how much. So let's write down the equilibrium constant expression for this system. And so we have K is equal to products over reactants, and the activities for both solids is 1. So we're just going to put in 1 for both of those solids. And that leaves us with only the partial pressure for carbon dioxide. Now, when we add up the initial plus the change, we're just going to end up with X at equilibrium. And again, these two are just going to be 1, so I've left those blank. So we plug in X for the partial pressure of carbon dioxide, and the equilibrium constant is equal to 1.04. So that just means that X is equal to 1.04. And it also means that the partial pressure for carbon dioxide at equilibrium is 1.04 atmosphere. So another really central concept, and I know that we've talked about this before, is that the system has to have at least some of everything at equilibrium. What that really means is that as long as we have a little bit of each solid, the system is going to have the same equilibrium partial pressure for carbon dioxide gas. So we can begin with a lot of calcium carbonate, or we can begin with a little bit, but as it decomposes, we're going to get the same partial pressure for carbon dioxide. And in the process, we'll make some calcium oxide. So here's a question. If we were to add some more calcium oxide, for instance, to this system, if we were to add some calcium carbonate to this system, either one, as long as we didn't change the volume, would the partial pressure for carbon dioxide change? And the answer to this is no, because remember, as long as there's even a little bit, the activity is 1 for both of those solids. There's no way adding a little bit more solid, whether it's calcium carbonate or calcium oxide, that doesn't show up into the equilibrium constant expression at all. And so it's not going to change the equilibrium partial pressure for carbon dioxide. Next up, the reaction quotient Q for non-equilibrium systems.